Hi, folks. I want to make you that video talking a little bit about section 3.5 just to kind of help with any issues that come up with it. So I talked a little bit already about what this section is going to discuss, but I want to reiterate that and kind of give a introduction here a little bit. So the goal of this section on function transformations, it's going to take some of our functions and tell us how they're manipulated, how they're moved around. We can think of it that way graphically when we perform operations on or in that function. So if we take a fairly base function like the square root of x, this generally works, or we'll generally play with it by starting with a basic function that we know, like x squared, square root of x, x to the third, absolute value of x. One of those functions that we should know how it behaves, and look at what performing operations, specifically addition and subtraction, or addition, subtraction, multiplication, and division, how the graph is affected, and thus the function behavior is affected when those operations are done around and within this function. So if we look at, say, that square root of x graph, we know roughly what that square root of x graph looks like. And it does kind of look like a parabola that has been flipped on its side. And you want to think of it as the positive part of the parabola being rotated, as opposed to the negative part of the parabola rotating down this way. You want to kind of see that positive part of the parabola flipping to make this, because in the inverse function, that's actually what happens. But our goal is going to be to determine how this graph is going to be manipulated, transformed by adding, subtracting, multiplying, and dividing within and outside of this function. So for example, if we want to know what it's going to look like if we make a new function that is f of x, say, plus any particular number. I'm going to pick plus 3 here. And this is a new function that we're building, g of x. And I want to graph that new function, g of x, in this orange. If we wanted to look at what that would look like in an equation format, well, this is our f of x and then plus 3. Our f of x is the square root of x. So this would just become the square root of x plus 3. So you might see g of x defined this way. You might see g of x defined as the function of reference plus 3. Either way, it's talking about the same thing. So real quick, this is usually one of the nice ones. What's this graph going to look like? Well, we're still going to have the same inputs and outputs for x. If we put in, say, 4, the square root of 4 is still going to be 2. The square root of 9 is still going to be 3. The square root of 16 is still going to be 4. The only difference is this function is going to add 3 to those output values. So each of these output values is just going to increase by a factor of 3. So this point here at 0, 0 is going to move up to an a y value of 3. The point 1, 1, you put a 1 in here, square root of 1 is still 1, but plus 3 is going to move that up to 4. And each one of those points is going to become 3 units higher. So it's going to look very similar. It's going to be the same basic graph. It's just occurring 3 units higher. We usually refer to translations like this as vertical shifts. And we could say here a vertical shift by positive 3. If this wasn't a positive number, say it was a negative 4, then the same thing would happen. The function would just drop 1, 2, 3, 4 units. If it was negative 1/2, it would just drop by half a unit. So it would be, roughly there. So whatever this value is, the vertical shift is probably one of the nicest of the translations. It just either lifts or drops the function without changing its shape. There's no compressing, no stretching, no warping of the function occurring, just a strict change of position. Similarly, if we build another new function, I call it h of x, and let that h of x be this function, so f of x, again referring to this square root function, but this time I want to put f of x minus 1. Now the distinction here is really important. The distinction between this 3 being added outside of the function, or if you prefer, after the function takes place, the square root occurs, then we add 3, versus this function where the x minus 1 is happening before the function takes place. It's inside the function. So if we were to write this out as just any equation notation or algebraic notation, that square root of x, that minus 1, would be occurring inside the function before the function takes place. Now, the reason that causes such a different reaction is because here, this plus 3 is happening to the outputs of the function. It's happening to the y values. Here, this minus 1, it's happening to our inputs. It's happening to our x's before the function ever takes place. So while this plus 3 moved this moved this up and down, this minus 1 is going to move us left and right. Adding or subtracting values inside the function or before the function will move it left and right. Where adding and subtracting outside the function or after the function will move the function vertically up and down. So that's one issue. The other issue, it's almost more significant, is any of this stuff that happens inside here, it's going to seem to happen backwards. Now, there's a couple of reasons that we can kind of conceptualize. There are a couple of ways we can conceptualize why that happens. One of them that I like is that if we imagine this, what this subtracting 1 is doing, it's taking all our x values, lowering them by 1 before the function takes place, so before there's any graph. So instead of the graph, instead of this curve going in the going -1 this way, what's shifting -1 this way is the axes themselves. So if we imagine, say, this black stayed where it was, and then the x and y axis moved this way 1 unit, it would make the graph appear to have shifted 1 unit in the positive direction. So this x minus 1, it will look backwards, and it frankly should. It's going to move the function in the graph of the function in the positive direction because it's technically moving the x-axis backwards out from under it. And instead of redrawing the whole axis, the whole system shifted over, it's just easier to represent the function having moved the other way. Hopefully that seems somewhat reasonable. We could also just say plot some points. If we tried to plot what happens when x equals a 0, well, 0 minus 1 would be -1. The square root of -1 isn't real. So there's no point on the graph. At -1, -1 minus 1 is -2. Square root of -2 is also not real. You can't have any points out here. But as soon as we get to x equals 1, 1 minus 1 is 0. It's going to act like it's a 0 when x is 1. So when x was 1, this thing acted like the 0. When x was 2, it acted like a 1. When x was 3, it acted like a 4. So everything, all the x values one level further, acted like they would have earlier. So everything's happening further down the axes. So however you want to conceptualize that, um, do make sure everything that's happening in here, we conceptualize as happening backwards. The other way to conceptualize it is if we try to solve for where the points are, if we tried to solve this, we'd have to add 1 to both sides, right? So that +1 is the movement of the graph in the positive direction, if you want to think about it that way. However you want to think about it, we do have to remember that whatever's happening inside the function, before the function, is always happening backwards. But as long as it's an addition or subtraction, it is going to be one of these horizontal shifts. We do call these horizontal shifts. And again, if this was x plus 3, it would still be in reverse. That x plus 3 would mean the graph happened at 1, 2, 3, back 3 points. So it would be there. If it was x minus 2, it would go 1, 2. It would start here. X minus 7, oh, sorry, let's say it was x plus 7, we'd be way back here, 7 units. But it would just move it right and left, however many units are indicated here, but again, backwards. Because of that, we'll often see our kind of generalized notation. Let me put a generalized notation thing down here. Often we'll see an x minus c plus d. Notice this plus d, since it's outside the function, that plus d is these vertical shifts, and it happens in the normal natural direction we'd think. So if it's a positive 3, it's going to go positive. It's a negative, it's going to go negative. But we often list this horizontal shift with a negative already in front of it. So what's actually causing the positive 1 shift is the positive 1 that's being subtracted here. So if you're wondering why that negative often comes up in the generic form or the abstract form, that's why. It's to kind of say that, hey, this C is the amount of shift. And that opposite sign has to occur. It's actually kind of like when we're solving with factoring and when we're finding the vertex of a parabola. All those reasons why that negative changes are similar. But either way, these two shifts are the way we can move a function left and right or up and down without changing its overall shape, without warping or deforming it. If instead we say make another function, call this one s of x, and let that be, say, 2 f of x, this time that amount that we're putting on the outside, instead of having it be added, it's being multiplied. So that's going to affect it differently than the adding did, but because this plus 3 was outside, you remember it affected our y values. Similarly, this times 2, the function has already occurred. Our y values have been generated, and those y values are being multiplied by 2. So it's only really affecting us in the y direction, in that vertical direction. So what's this going to do to our basic function? What's multiplying this 2 going to do to our square root of x? Again, in kind of algebraic notation instead of function notation, it's the 2 times square root of x. It's going to take each of these y values and double them. Now that's going to look surprisingly different from adding a constant amount. Adding a constant amount took every one of the values and moved them the same amount. That means it didn't change the shape of this thing at all. Multiplying everything by 2, how much of an effect that's going to have on our graph depends on the specific value of our graph. I'll show you what I mean. If we take each of our y values and multiply them by 2, this y value of 0, when multiplied by 2, is still 0. Nothing happens. The point is still right there. When we look at the point, say, 1, 1, you multiply 1 by 2, and okay, you get 2. So it did go up some. but only increased by a value of 1. It went from a y value of 1 to a y value of 2. Okay, so it's 1 more than it was. But say we get over here to a y value of 2, when we double that, it becomes 4. So it increased by what? By 2 that time. So as our values get higher and higher, the effect of doubling them gets more and more dramatic. You know, if we're way out here where say the y value is 10, when we double that, we go up to 20. So not only is it going to make it stretch out further, it's going to make it stretch out further and more and more and more and more as it goes up and up and up. Still the same basic shape, still the same basic behavior, but stretched out. I always imagine silly putty here. If you remember silly putty, when you used to rub silly putty on something in a magazine or a newspaper, and then stretched it. The stuff in the middle doesn't deform that much, but the stuff on the top and the bottom deforms a lot. So this multiplying by 2 is going to stretch this thing way out, doubling all of our y values. So same general shape, same general behavior, but it's going to tend to make it kind of, you can think of it as becoming more extreme, more stretched out. If this was, say, a 1/3, it would do a similar thing, but instead of multiplying everything by 2, it would multiply everything by 1/3. So it would be shorter instead. It would be lower, closer to the x-axis. All these points would be a third of their current height. So again, smaller numbers, taking a third of it doesn't move it that much. Larger numbers, taking a third of it moves it quite a bit more. So it would be lower and more gentle, if you don't mind calling it gentle. And just like we called the up and down shifts a vertical shift, we often refer to these, because they are still affecting us vertically, as a vertical stretch. So this would be a vertical stretch by 2. This would be a vertical shift by 3, a horizontal shift by 1. The last one, you can probably imagine, the last one of our main pieces, we added on the outside, we could have subtracted. So adding and subtracting on the outside make us move up and down. Adding or subtracting on the inside made us move right and left, but backwards. Multiplying on the outside stretches us vertically, or can compress us if it's less than 1. The last thing we have to do is look at what happens on the inside. So I'm going to use pink for this one. So let's say we had another function, and this function had a 3 times our x on the inside of the function. So that was, say, the square root of 3x. Again, notice it's happening before the function takes place, where this one's happened after the function took place. It's happening inside the function as opposed to outside the function, which other language you prefer. I always like before. Actually, I like both of them. I like go back and forth. So in the same way that this affected our y values, so this affected our y values, this -1 on the inside affected our x values and backwards. So this is going to do the same thing. It's going to affect our x values, and it's going to do it in reverse. So instead of taking our x values and multiplying them by 3, we're taking those x values and dividing them by 3. You can think of it in terms of solving for this. We'd have to divide that 3 off to get it away. You can think of it as the x-axis becomes 3 times as long. It makes it look like the function has compressed by a third if we don't change the scale. However you want to think about it, this is happening in reverse. So instead of this thing becoming stretched out 3 times, it's all going to happen much faster. It's going to be squished down. Yeah, it's going to be squished down and happen over a shorter period. And actually, one of the things that people like to think about in terms of this 3, you can imagine it making the function happen 3 times as fast. So instead of this fairly slow growth here, it happened much faster. It got higher and it started to flatten out much sooner. It happened 3 times as fast. It's actually one of the reasons we use times for multiplication. So sometimes this can help if you think of this in terms of speed. Here it went twice as far, so it stretched out. Here it happened 3 times as fast, so it appeared compressed, if that helps. And again, if we wanted it to stretch out, if we wanted it to happen really slowly, say, we wanted that to be, really gradual, instead of speeding it up, instead of multiplying it by 3 times, we could have multiplied this by, say by 1/3. Then it would be 1/3 of x. Then it would happen real slowly and real gently. So we can have it slow down. We can have it stretched out horizontally if we want. It just takes a multiplying by something less than 1 to do that. And again, I think thinking about it in terms of speed can really help with those, particularly if you plan on taking Math 112. In Math 112, we'll often think about that constant multiple on the inside as affecting how fast our waves oscillate. So that can be a helpful way to think about it. Do keep that in mind, by the way, all of these graphing tools, this is how we graph almost everything in Math 112. So if you plan on taking Math 112, you really want to get good at this section. We'll reinforce it in Math 112, of course, but the more you can take along in there, the happier you will probably be. So we often consider this vertical stretch, that multiple on the outside, to be an A, and that compression factor there to be a B. Compression factor is usually what I call it in Math 112. Here, you'll often refer to it just as a horizontal compression. And again, the reason this is a compression where this is a stretch, whole numbers here will stretch those y values out, where whole numbers here will compress it left and right. But consequently, if this is a fraction less than 1, or any number less than 1, this is going to be visually a compression. We often still call it a stretch, just a less than 1 stretch. But it would compress if this is less than 1, where this horizontal compression, it would be a stretch if this value was less than 1, but still positive. All right, last but not least, before we kind of start to leave these a bit, there is one other thing we tend to look at for stretches or for transformations, and that's what happens with negative values. So real quick, if we look at, instead of multiplying this by something like 2, let's say we just put a negative sign in front of it, and that's the new function we make. I don't actually tend to think of this as a different version. It does the same thing that happened here. You're taking the y values and multiplying by something. Here we multiplied by 2, so they ended up stretched out. Here we're multiplying technically by -1. So all of our y values, all these black y values, are going to become, instead of positive numbers, they're going to become negative numbers. So it's just going to be down here. Oops. Mirrored essentially down there. It does have a different name, which is why we're handling it a little separately. This is referred to as a vertical reflection. Some people just call it a vertical flip, but technically reflection. So let's say this was a -2. We often think of that as 2 different transformations. One, the negative, causing it to be flipped, and then the 2 is going to cause it to be stretched out. Whether you like to think of it in those 2 stages or like to think of that -2 as just being, we're multiplying by -2, so we're going to get stretched out values that are flipped, whichever way you want to think about it, whatever works for you. Similarly, running out of colors. That brown might work. Let's say we have f with that -x on the inside instead. Again, very similarly, because it's happening inside, it's going to be a left and right argument instead of an up and down argument. It's going to be like these compressions in that we're multiplying by the value. Here, that multiplying by 3 turned us into a dividing by 3. Here, multiplying by -1 is going to technically turn into dividing by -1, but multiplying by -1 and dividing by -1 perform the same behavior. And it's going to do something similar to what this vertical reflection did. It's going to take all the x values, multiply them by -1, and take all the x values that are on this graph and shift them to the other side. So it's going to, oh, I want to try to draw that better. It's going to take this, it's harder to draw in that direction, and reflect it that way. Let me try that just one more time. Try to do it this way. That's a little bit better. Anyway, so it's going to take everything on this side, flip it to the other side. If there was stuff on this negative side, that negative of the negatives would turn them positive. So it's, again, just flipping, mirroring this whole graph, but it's mirroring it in the horizontal direction. So often referred to a horizontal reflection. And similarly, if this was, say, the square root of -3x, whether we want to think of it as we're multiplying by 3 and then flipping the whole thing, or flipping the whole thing and then multiplying, or sorry, dividing, got to do it backwards. So whether we think of it as dividing all these values by 3, compressing this down, and then flipping it, or whether we think of the negative flipping it and then compressing all those down, we end up with the same image. So no matter what, we end up with that same, no matter how we think about those, as multiplying by -3, so we got to divide by -3, or if we think of it as multiplying by 3 and then separately think of this horizontal reflection, we end up in the same place either way. So if any of this brings up any questions, let me know. But all of these separately is one thing, but kind of the end goal here is to be able to take a problem like, say, y equals 3 square root of -2x plus 4 minus 1, consider all of those changes and figure out what this graph looks like, just knowing what the square root of x looks like and knowing what those translations do, what their job is. So let's look at what's going to happen here. Do pay attention to this order. This order can be helpful. I'm going to start with the horizontal shift. It is fairly important to do that horizontal shift first. I'm going to say you really should always do that horizontal shift first. That horizontal shift says we're going to move in the negative direction. Again, it is a +4, but remember, everything on the inside is backwards. So we are going to shift in the negative direction 4 units. So that's the first one I want to imagine. Then what's going to happen here? That multiplying by 2 is going to compress us by 2. So it's conceptually going to have all values. So it's squeeze us by 2. And because it's negative, and it's going to flip us left and right. This 3 is going to be a vertical stretch by 3. So we're going to become stretched out up and down, tall and thin. And this -1 out here, I should have had my colors match the other page, but I didn't. This -1 here is going to push us down 1 unit. Now notice I only underlined these two really. It is important to do this horizontal shift first and this vertical shift last. So if I wanted to say 1, and then they call the compression 2, the flip 3, the vertical shift 4, this would be the 5th transformation. So it is important to do the horizontal shifts first and the vertical lifts or the vertical shifts up and down last. Really, these other ones, the compressions, the stretches, and the reflections, you can technically get away with doing in any order you want, mostly because of multiplication. You know, how you can multiply in any order you want. But it's really important that this horizontal shift occurs before this compression does. And it's really important that this vertical shift happens after the vertical stretch does. So the order I tend to recommend is do the horizontal shifts first. And since you're dealing with stuff on the inside anyway, do the horizontal compressions, then do any reflections, horizontal, and then presumably vertical if you've got any. Since you've now been looking at vertical reflections, do the vertical stretching, and then lastly, do the vertical shifts. So that's the order I tend to recommend, but really the important ones, this has to happen first, this has to happen last. And it's really an order of operations issue, making sure the addition and subtraction is separated properly from the multiplication and division. So if we wanted to look at what this graph was going to look like, we know the square root of x normally, we know how it normally looks. And I'm using the square root of x as an example. If this was x squared, we'd start with how x squared looks. If it was absolute value of x, we'd start with that v for absolute value. So this is just giving us a base function. Sometimes you'll even see problems on the homework and on tests and quizzes where they don't even give you the algebraic form of the function. They just draw it. They just say, hey, our function looks like this. And they say, okay, given the translations, and usually those translations are in this kind of f of x plus 3, f of x minus 1 form. Given those translations, what's going to happen to that graph? So you're just asked to go, okay, the horizontal shift's going to move it that way, the vertical shift's going to move it this way, then it's, say, going to stretch out from a vertical stretch, and then a horizontal compression is going to compress it. So we can even do all these things to an abstract, graphically defined function if we need to. So keep that in mind. This is just the square root of x is a nice example. So what's it going to look like here? Just drawn fairly roughly. Well, it's going to move that way 4 units. So it's going to be this way 4 units. So it's going to be over here at 4. It's going to be compressed by 2. So it's going to happen fairly tight and fairly stretchy. So I'm actually going to give myself just a reference here in that red. So it's moved back that way and it's become fairly tighter. So I've made this try to look tighter than that, by squishing it a little bit. Then it's going to flip left and right. So it's going to flip to, oops, not that way. So it goes this way. Then it's going to flip left and right. So everything that's on this side is going to flip over here to positive 4. Everything on this side is going to flip to the other side. So instead, it's going to be there. So this is gone. So that's the compression, making it happen a little faster, making it a little squishier. And then the flipping it from here over to there. Vertical stretch by 3 is going to take this thing and stretch it out. So it's going to make it happen really stretchy. So all the y values got tripled. So all those y values stretched out. And then it's going to drop 1 unit. So this point and all the other points are going to drop down 1 unit, and everything's going to be basically the same. It's just they're all going to be 1 unit lower. So up to my ability to draw that, all these points went down by 1 unit. Oops, that one might be a little long. And that's where a graph's going to lie. So we might, after thinking about all those, want to redraw it all at once. But we're going to go back that way 4, squish it, flip it, stretch it, drop it. So it's going to be like that. So that's what this function looks like. We could even track a particular point. This is getting to be our class hour length. So if we take a point here like 9,3, we could do all this to that point 9,3. That point 9,3 is going to go to the negative by 4. So that's going to turn that 9,3 into 5,3. So when it shifts this way, it turns into 9,3. Then it's going to be divided by 2. So it's going to turn into 5 halves 3 when it compresses. So that's it. It's moving over here and then getting squished. Then it's going to flip sides. So the positive's going to become negatives on the x's. So that point's going to go to negative 5 halves 3. So it's going to flip over here. So it's going to be, somewhere around there. That's done with our x values. Then what's going to happen to the y values? We're going to triple them and subtract 1. So that y value of that negative 5/3 is going to not change anymore. Our y value, multiply it by 3, turns into a 9. And then subtract 1, it's going to turn into an 8. So negative 5/3, 8. That's all of those transformations. So what happened to this point at 9,3? It got shifted by 4. Yeah, it got shifted by 4 to 5,3. Then it got squished to 5 halves 3. And it flipped to the far side to negative 5 halves 3. Then it got stretched to be triple the size up here at negative 5/3, 9. And then we subtracted 1 to get the negative 5/3, 8. So that point ended up, I'm going to say roughly there at negative 5/3, 8. So we could track specific points, we can move graphs, we can do a lot with this skill of being able to transfer these graphs around. So play with this. A lot of you have already started playing with this, and that's great. Maybe this helped. Oftentimes the compressions and the stretches can be a little strange, particularly the compressions happening backwards on the inside. If it helps, you really can think about both the horizontal shifts and horizontal compressions as happening to the world the function is in. So if the world the function is in triples in size, the graph appears to be 1/3 the size. If the world the graph is in moves in the negative direction, it makes the graph look like it's moved in the positive direction. It's actually a pretty common concept in mathematics, to the point that it appears in Alice in Wonderland. If you've ever read Alice in Wonderland, it might be interesting to know it was actually written by a disgruntled mathematician. This was an old, very stern mathematician who was big on things being geometrically defined. So the new kind of modern mathematics of his time bothered him a lot. And one of the things that bothered him is the idea of a non-universal reference. So the idea that, whether or not something grew or shrank depended on your point of view irritated him. So in his book, Complaining About Modern Mathematics, he had that scene with the eat me block of stuff, a cake or whatever it was, and the little potion, drink me, where Alice would grow and shrink. But if you read the text at first, there's confusion whether or not she is growing or if the room she's in is shrinking. Which is happening? Am I getting really big, or is this room shrinking around me? And that's what he's talking about. He's talking about this distinction about those not being different. Did the function get 3 times as wide, or did the world the function's in become a third the size? Did the function become squished to half its length, or did the world the function's in triple in width or double in width? Those things are the same, mathematically speaking, unless you're Lewis Carroll, which was actually his pen name. I can't remember his real name. Anyway, interesting facts about Alice in Wonderland. A lot of interesting mathematics in there. Either way, play with this section. Let me know what you think and if you have any questions. And as always, have a wonderful day.